So this is the last chapter of the semester, chapter 19, looking at strike-slip tectonics. Start off by talking about two types of situations within a strike-slip fault, because strike-slip... Second, having a noise problem. Okay, hopefully there's no... Okay, the feedback's gone. Within a strike-slip fault, we're all familiar with the idea of, hey, it's two blocks sliding past each other. But these faults are not straight lines the whole time. Anytime there's a bend in the fault and it's not straight, we're either going to get compression or tension. Now, because these are strike-slip faults, it gets called transpression. This is where the strike-slip movement goes around a bend such that it's creating shortening and compression and pressure. This is going to produce uplift. If the bend is going the other way relative to the strike-slip motion, then we're going to get extension. We're going to get tension. So it's called transtension. And this will produce subsidence. So one produces uplift and the other produces subsidence. And we will see drawings and Google Earth images and lots more about this as we progress through the chapter. But those two terms are important. So if we look at the North American plate and where it bounds the Pacific plate, we find the San Andreas Fault. I'm sure everybody has heard of that by now. I hope so, because I've talked about it in class, but also probably you've heard of it before this. We can see a trace of the San Andreas Fault right here, and we see it's not a straight line. Even at this scale, it's not a straight line. We have two large bends, one right here and one right here, and then especially as you move into smaller and smaller scale, instead of looking at a map at this level, there'll be other bends that occur throughout the San Andreas Fault. And every time there's a bend, you're going to either get transpression or transtension. Now, if we see the Pacific plate is moving up to the left and the North American plate is moving down to the right, you can see that right here, where my mouse is, right about where this other fault splays off of it, there'll be a lot of pressure build up, because those plates aren't going to slide past each other very well right there, because the Pacific is trying to move up and it's hitting it, and the North American plate is moving down and it's hitting it right there. Lots of pressure, lots of uplift. You notice here's the Great Valley, and at the bottom of the Great Valley where that bend is, there is uplift. This other curve, there's going to be some pressure as well. It's trying to move up to the left, trying to move down to the right. Any place that has a bend in the opposite direction is where we would see the tension. Now if we look at another fault, the Alpine Fault in New Zealand, we can see this horizon marker is basically a bed or a formation that has been sheared off. So we see part of it down here to the southwest and part of it up here to the northeast. And we can see that there's a subduction zone down here in the bottom left by the letter M, and a subduction zone up here to the right by the letters TK, and in between them is a transform fault section. So with that, we're seeing, again, plate boundaries with some subduction connected by transform faults. Now we always use the words strike-slip faults and transform faults. There is another term that you should know called transcurrent faults. Both transform and transcurrent faults are types of strike-slip faults. Transform faults are just the more commonly talked about faults. These are faults, they are transformed, they're side-to-side sliding motion. But most importantly, the end of the fault is a junction either with another fault or with a plate boundary, which is going to be a fault. So really, you could simply say ending at another fault. And it's important to note there's equal distribution of deformation, movement, slip, along the whole length. This is what you would have if you have, say, a textbook sitting on the table. Think of the contact between the book and the table as the fault. So it's more like if you have two textbooks and you stand them up on their edge and you have them against each other. The contact between the two textbooks is the fault. If you slide one book past the other, that's that whole strike-slip motion. The whole book moves evenly. So the distribution of deformation, the amount of slip, along the whole length is the same. The books moved consistently within that book. There was no stretching or compression of your textbook. It's the same as before, it's just in a new place. A transcurrent fault, on the other hand, does not end at the junction of another fault. It ends either just by dying out or in horsetails, which I'll show you a picture of what we mean by that shortly here. But the important thing is it's not junctioning with another fault. It's just dying out. And there is unequal distribution of slip along the length. The only way that this can happen is if there is some elastic plastic type deformation. Elastic if it's temporary and it will recover, plastic if it's permanent flow and permanent deformation. Think of this like you take a big chunk of Play-Doh and press it against the cover of your book, and then you shear it along the book. Some of that Play-Doh stays behind or doesn't move as much. The chunk of Play-Doh deforms dramatically, and some of it near the leading edge moves and slides along the book much more than the Play-Doh towards the back that was getting smeared. So there was an unequal amount of slip along that transform fault. That strike-slip fault. It was a transcurrent fault because the slip was uneven. As you can see there, it's easy to mix the terms, but if you slow down and make sure you're keeping them straight, and especially if you see it in literature and you see transcurrent fault, you can be like, okay, so let me look at my notes. Oh, that's when it does not end in another fault. We can have faults at both a convergent boundary and a divergent boundary. So here we have a convergent, so there's subduction. On the right we have a divergent. There's like mid-ocean ridges, rifting going on. And we see in both cases what connects two segments, whether it's two segments of subduction or two segments of extension and rifting, are little transform faults. Sometimes they're little and short. Sometimes they're very, very long, like the San Andreas Fault is quite long. But it's connecting two segments of subduction. And the way it happens is those accommodation zones where there's small faults and lots of distortion and deformation that occur start connecting and joining and becoming a transform fault. So what starts out as just an accommodation zone becomes a transform fault. Now, this is a transform fault, not a transcurrent fault, because once it turns into this fault, there is even distribution along the fault. The whole thing is moving, and it is ending at plate boundaries. Each ridge is a plate boundary. If we look at this picture here, right where this text that says New Mid-Ocean Ridge is one plate. Call it plate A. On the other side is a different plate. It's plate B. The transform fault extends from the ridge to the other ridge. So since it's extending to the ridge, which is the boundary between plate A and plate B, it fits that definition for a transform fault, ending at another fault or plate boundary. On the other hand, the transcurrent faults end either just by dying out, lots of plastic deformation for a fault to simply die out. At one point along the fault, you have displacement of, say 10 feet. At the far end, there's no displacement. So that means somewhere in the length of that fault, some of the rock is compressed and some of the rock is stretched for it to actually match up by the end. The other method for one of these transcurrent faults to die out is the horsetails. Horsetails are a set of curved normal or reverse faults that bend off kind of like a horse's tail. So here we can see the top block here is moving to the bottom right, and the bottom block is moving to the top left. And the curvature is such that we get normal faulting. So we get the series of curved normal faults, and that is the end of this transcurrent fault. If the curvature happens to go the other way, because we still have the top block moving down to the right and the bottom block moving up left, but the curvature is such that now we have compression. We get reverse faulting. So depending which direction the curve of the horsetail is, you either get normal faults or reverse faults. Either way, this is the termination, this is the end of the fault. And that's why it has to splay into multiple smaller ones, is to relieve all of that pressure, whether it's the compression pressure that was giving you the reverse faults, or all of the tension giving you the normal faults.